So we've been talking about quantitative data, a big part of what we've done so far this year, but it's always only involved one variable, okay? So like, you know, we're given information about one variable, a whole bunch of data values about one variable, and we found like the mean and the median and the standard deviation and the percentile if necessary, if z-scores, okay, but it always dealt with one variable. Much of what occurs in everyday life is relations between two variables. So when we did one variable work, we were studying what was called univariate data, okay? And what we're going to look at now in this unit is bivariate data, where we're looking at the relationship. Essentially, we're looking at the relationship between two variables. Okay. And just like we did with univariate data, there were types of graphs we could use to analyze them or study them. And the main graph that we use for two quantitative variables to study the relationship between them is a scatter plot. Which is a visual way that shows us a relationship between two variables. And then, of course, we're going to look at a bunch of measures, just like we did with univariate data. So the example we're going to use for this lesson, this is a very popular grocery store in Texas. I don't know if you've heard of it, H-E-B. I've never seen one. I've never been in one. But anyway, that's... so you can imagine any grocery store. We're going to look at the relationship between household income in San Antonio, a specific city in Texas, as well as the number of organic vegetables offered at these H-E-B grocery stores. Okay? And of course, why are we doing this? Because we want to see if there's some kind of relationship. We want to prove if there's some kind of relationship, if there's some kind of issue that perhaps can be solved, that perhaps there's a problem here. And we're going to see that actually in this example. So we have two variables, income and the number of organic vegetables offered. Right? The explanatory or independent variable, you should be familiar with independent and dependent variable. That's the variable that predicts the dependent variable or the response variable, or it explains it. Okay? And this is always, oh, I've got that there. This is the x. Okay? This is the x variable. The response variable, well, that's the one that gets explained. Okay, its values depend on the independent variable or the explanatory variable, and it is the y variable. We use x and y because obviously we're familiar with xy coordinate grids. Okay, I mean, a lot of the graphs that we study, not just in mathematics, but in statistics as well, are all based on an xy coordinate grid. So in this example, I told you the two variables, this and this. Which one do you think is explanatory and which one do you think is response?
Average household income.
Okay, and why?
Because the organic vegetable offered is dependent on the household income.
Yes, yeah. Or the household income will help explain the number of organic vegetables offered at a specific grocery store. Okay. So yes, average household income. is the explanatory. Because what are we really trying to see here? Well, we're trying to see if, like in higher income areas, are there more choices offered? Okay, because I guess organic is considered healthier, right? So does that mean that people with a higher income are getting access to healthier foods where people with the lower income are not? Okay. Explains or predicts the response variable, which in this case is number of organic items offered. Okay. Because it's the variable attempting to be predicted, or it's the one that depends on the explanatory variable. Okay. So it depends on explanatory variable. So we need to be familiar with the words we use in statistics, like in science, generally independent and dependent are used, but in statistics we use explanatory and response. Okay? So we want to make sure that we have the variables set up properly before we show them visually. Anyway, here's all the data. So we're going to take all this data, all the household incomes, all the corresponding number of organic food items offered at the grocery store in the area, and come up with a visual presentation of that. And it looks like this. And this is a scatter plot. Okay. I mean, basically, you're just plotting, you're treating the explanatory response variable as X, Y coordinates in your plotting. And then from the plotted points, we can look for patterns, we can calculate measures. So how do we describe scatter plots? Well, we want to talk about the relationship between the two variables, between household income and how many organic items are offered at a grocery store. So, I mean, what can you see right now? Just ignore this line for a second. Just look at the points. What would you say? It's going up. So what does that mean? Like, tell me in context. What's that?
Proportional, something?
Yes, it is. But tell me, use the names of the variables. So as the household income gets bigger or larger, what happens?
X and Y. Oh, X and Y.
Use context. Don't tell me why. Tell me the name. What is the action? Yes. Organic items offered. So as the household income goes up, more organic items are offered. That's what we can sort of see from here. Okay. A word we use to describe the relationship, if one goes up, the other goes up, or if one goes down, the other goes down. Or if one goes up, the other goes down. Did I just say that twice? I didn't mean to. Anyway, the word that we use is called correlation. Okay, which is really just describing the relationship. So you can see here a bunch of scatter plots. Okay. And it shows you the strength of the relationship. Okay. Among other things. It also shows you the sign of the relationship, SIGN, but we'll get into that in a second. So if there is a perfect linear pattern that climbs, okay, and you can put a line right over top of all the points that you plotted, that's a perfect positive correlation. Okay? If, as one goes up, the other comes down perfectly, it's a perfect negative correlation. Those are very rare. Okay? Strong positive correlation looks like a line, but not forming a perfect line and going up. Strong negative, close to a line, but not quite, and going down. And then, of course, the weaker the relationship becomes, the more scattered the points become. Unless they're completely randomly scattered, then that means that there's just no relationship between the two. There's like no correlation. Okay? So, to be positive, as one variable increases, so does the other. Which is what we see in this example. If it's negative, we still say as one variable increases, this time, though, the other variable decreases. Okay? So, as mathematicians, we want to quantify this. Okay? And one way that we know how to quantify relationship is using lines. Okay? And what we do in statistics is we want to fit a line to the relationship that we see by all the points. Okay? In the first and last examples, it's pretty easy because they form a perfect line. Like so. And what can we do with lines? Well, we can quantify them by making defining equations for them, which helps us make predictions and helps us answer questions. Okay? If it starts to get a little weaker, the correlation, well, we need to sort of draw a line that half the points are above and about half are below. So maybe something like that. And similarly here, something like that. But notice the points, they're going to be many of the points are going to be a little further away from this line. So our predictions aren't going to be quite as strong. And that's going to happen if it gets even weaker. Again, I could, something like that, for negative, something like that, where about half are above, half are below. And for no correlation, you can't draw one. Because there's no relationship, so why bother exploring anything? Okay? So we'll get into a little later why it's called least squares regression line. But basically, like it's a line right now, but we're going to talk about, well, how do we know where to put the line? Like, you know, how do I know it's like this and not like that? right? So we'll talk about that as we proceed through the unit. I mean, there's not a difference between the two, but it still can make a big difference. So we were asked to describe the difference between strong and weak correlations. So in a strong correlation, what do you notice about the points in the line that we placed on? What's the relationship between the points in the line? They're close, okay? And the stronger the correlation is, the closer those points will be to the line, okay? So strong correlation, the data values or the points are close to the, and often we'll just use the abbreviation for least squares regression line. Okay? Instead of writing the whole thing out all the time. Or we'll just say regression line if we assume we're talking about least squares. And then a weak correlation, obviously. Data values are further away. Some may be on the line, but more of them are further away than a stronger correlation. So what is the quantity that we use to actually measure correlation? And it's suppose, jump ahead myself here, because we want to talk about certain characteristics of this least squares regression line. And here's another acronym, okay? DOFS. So that means we want to talk about the direction, okay? Is it positive? Is it negative? Are there any outliers? The form in DOFS represents whether it's curved or whether it's straight. Okay, most of the ones we're going to deal with will be straight or linear. And then finally, the strength. Okay, well, right now you don't know much about the strength because we're only sort of guessing at it. Okay, but if we were to describe the relationship, okay, so the relationship between income and organic items offered is, now you can deal with 3 of the 4 in one sentence. This, actually you could probably put in the 4th one too. But what's the direction? Positive. Is positive? Is it linear? Yes, because we can basically place a line over it. I mean, if a bunch of these points started going like this, we'd have a curved pattern. That's something different. Okay? Linear. And now this is where we're sort of guessing a little bit right now. There is a way to calculate it. Okay? How strong do you think it would be? Weak. You think it's weak? Medium or moderate? Moderately strong. I mean, it's not bad. Okay, I mean, obviously it's not perfect, so we can't say that it's really strong. Okay, sure, let's go with moderately strong. And we'll talk about in a second where we can use certain words. And then, well, actually, we can just finish it in one sentence. Any outliers that appear to you? Now, remember, when we talk about outliers, we're talking about the distance from the regression line. I mean, does any of them really far from the regression line? No, I mean, this one, yeah, but then that one's pretty close to the same difference, just like that one is. So there's really nothing that's sticking out. So with no outliers. Outliers. Okay. So how do we measure correlation? We talk about something called the correlation coefficient, and we use a lowercase r. And what it does is it measures the strength and direction. This number will always be from -1 to 1. Okay? 1 means a perfect positive correlation. -1 means a perfect negative, just like you see here. If there's no correlation, then it's 0. Okay? These are pretty rare. Well, not the no correlation, that's not necessarily rare. We're going to focus on the gray areas, right? Where it's like, okay, this one, pretty strong, 0.91. But the weaker one, under 0.5. And then you see similar going the other way with the negative correlations. Okay? So, you guys having fun? R is close to 0. We have a weak correlation. If R is close to -1 or +1, we have a strong correlation. If R is negative, obviously the correlation is negative. And if R is positive, obviously the correlation is positive. Okay? Now, in general, you can go by this guy. If R is, make sure I get my things right here, 0.8 to 1, or -0.8 to -1 for a negative correlation. We would say that's true. If R is from 0.5 to 0.8, or -0.5 to 0.8, we would say it's moderate. And finally, if R is from 0 to 0.5, or 0 to -0.5, we would call that a weak correlation. Okay. So just to give you an idea, let's see if I can find it. Where's the applets? Yeah, guess the correlation. Okay, so here, this is going to give you a good idea. There. If you were to guess a correlation, what do you think you'd guess? But definitely negative. Moderate, weak. Sounds like we're maybe leaning weak. Okay, so chances are under negative 0.5, like between 0 and negative 0.5, right? That would be considered weak negative, where one goes up, the other goes down. Take a shot. What do you got? Somebody give me a number. Negative 0.3. It's negative 0.546. Okay.
Negative, small,
Yeah.
negative 0.9.
Negative 9. Negative 0.9. 2. Did you have a 2? Even higher. Even stronger. Stronger negative. But we're close. Okay, let's see. You guys are getting it now. Ooh,
Positive.
definitely positive, but pretty weak, I'd say. Eh? Like, think about that first one. That was negative 0.5, and that was maybe moderate, but mostly weak. But that was still negative 0.5. So what would you say for this one? 0.1? 0.125? That's still 0.3. That's why I said get that other one. It's maybe a little bit higher than you think. Okay, like, so it clearly for 0 or 0.1, it's got to be pretty scattered. Let's try a positive one here. Okay, what would you say for that one?
Positive, strong,
Yeah, not as strong as that other one we had. 0.85. Anybody think it's going to, somebody thinks it's going to be 0.9. It is. It did reach, but we're pretty close with 0.85. Okay. I want to get one that's pretty scattered. Oh yeah, there's a good one. Oh. I mean, the first thing you got to figure out, is that positive or negative? Okay, we got some argument. Thinking more this way?
Yeah, we can do it right in the middle.
Yeah, like it would, looks like it may fit more like that than it would like that. Don't you think? Okay, take a shot. 0.2, negative? Anybody want to go closer to 0? Well, let's see what we got. They're saying it's positive and very weak. That's a tough one. I don't know. I see negative too. But remember, like if we said something like negative 0.1 or negative 0.0 something, we're actually close, right? Because I mean, this is really close to 0. Anyway, I just wanted to give you an idea of what the actual numbers mean. There is a formula where you use all the data values and you calculate the correlation coefficient. We're not going to worry about that. Okay, we're going to let the graphing calculator do it for us when necessary. But I do want to talk a little bit about the discussion. on the last page, just so you have an idea of describing a relationship. Okay. So from 1994 to 2020, a statistician collected 3 pieces of data each summer at a beach: the average temperature, the amount of ice cream sold at the local beach shop, and the number of drownings. Okay. So the first scatter plot uses the average temperature to predict the number of ice cream sales. One would think, using common sense, that that would be positive, right? The higher the temperature, more ice cream sales, and we can see that that happens. How would you, who's pinging? Stop pinging. Okay. Describe this relationship for me. 4 things. Positive, strong, no outliers, linear. The next 2 that were compared was the amount of ice cream sold and the number of drownings, which is sort of an odd 2 variables to compare, but anyway, we see that the relationship, the relationship is positive, linear, strong, moderate to moderately strong. Yeah, I mean, it's still pretty strong. Doesn't really look like there's any outliers. Okay? Which one makes more sense? The top one, right? Okay. Why does this one not make as much sense? This sort of goes into another area of statistics. What else could?
If there's more ice cream, there's more people.
So there you go. That's something that we call a lurking variable, which means it's some other explanation. Okay? So yes, there's an association between it, but does one cause the other? Highly unlikely. There's probably some other variable that's the cause for it. Okay? So good to keep in mind. Okay.